Okay, in this lesson, we're going to consider different types of circuits and analyze them for different properties. Hopefully you can recognize these symbols, right? Here I have the battery, the light bulbs, three of them here, right? And wires. I haven't put any switches into this. I'm just trying to focus on the arrangement of the loads in the circuit. So you've already learned the name for loads that are connected in the same path versus loads that are connected with different paths for electrons to flow. So hopefully you can recall the name of this type of circuit, right, and the name of this type of circuit. So pause the video, think of those terms, and write your titles here. Okay, so hopefully you decided this was a series circuit and this was a parallel circuit. Okay, so just to give you an idea of the scope of this lesson, we're going to consider each of the series and parallel circuits for these criteria here. So the number of paths for the electrons to flow, the electrical energy or voltage, the current that's flowing, as well as the effect of adding or removing loads, and whether the loads or devices are all on or off at the same time, or can be controlled one at a time. To help you understand this, as opposed to just memorize answers, we really want to build a deeper understanding. An analogy could be helpful. We could think of the electrons that are leaving the battery as cars, and the energy or voltage or potential difference of those electrons as being smarties. So ideally then we're thinking about electrons as cars leaving the battery, right, and moving through the circuit and returning to the battery. The idea is that the electrons or cars, right, gain their smarties, they gain their energy from the chemical reaction in the battery, and they move through the circuit with their smarties. When they get to a load, right, then the energy, some of the energy of the electron is used to light that light bulb. So electrical energy gets transformed into light, right, and a little bit of heat energy. So electrons or cars carry their smarties and dump some smarties right here, lose some energy right here at a load. Those cars continue along this path, and when there's another load, they dump more smarties. And they continue along the path, dump smarties, and then return to the battery where they pick up more smarties and gain their energy again. So this is the analogy, right? If you can think of the electrons leaving the battery, right, as cars that are carrying energy or carrying smarties, right? And when they hit a load, a light bulb or a motor, they dump smarties, they lose some energy. All right, so that's what we're going to think about with our analogy. And by the way, it's important to think the more smarties that they dump at a load, the brighter the bulb will be, okay? And if there's less smarties dumped there, then that bulb will be dimmer. So now let's analyze each circuit here first the number of paths for the electrons to flow. So we're thinking about the electrons or cars leaving the battery here, right? And just look at the path, okay? So we're not even thinking about the smarties. We're just thinking about the electrons or the cars leaving the battery, right? How many paths do they have to get back to the battery? And we see here there's one path, much like a racetrack, right? Whereas on this side, electrons that leave the battery might take this path, they might take this path, or they might take this path. So there's actually three paths for the electrons to flow. So in this case, we can say that there's one path here. So this you might think of as like a racetrack, right? And in the case of the parallel, there's going to be more than one. In our particular example, there were three paths, right? And we think of this more as maybe city streets, you know, the idea that you can travel different streets to get different, multiple ways to get back to the battery here. So there's three paths here. Okay, in terms of the electrical energy, the voltage, we're thinking about the energy of each electron, which for us in our analogies like the smarties. Okay, so looking at the series circuit, we think of the cars leaving with full of their smarties, and when think about the path that those cars are going to need to travel. how many loads are along this path? The fact that there's 3 loads here in this single path means that when the car gets here, it's going to dump only some of its Smarties. It's going to need to have some Smarties left to dump at this load and here. Okay, so the idea is that each car, let's say each car is carrying 12 Smarties, it's going to have to dump 4 here, 4 here, and 4 here, assuming these bulbs are all the same resistance. It's going to dump Smarties here, here, and here. So the Smarties get shared, right, to the loads along the path, along the circuit. So the electrical energy or the voltage here is being shared. Whereas in this path, in this circuit, the parallel circuit, electrons or cars leave the battery, right, full of their Smarties. And each car, let's say again, has 12 Smarties in it. The electrons that travel this way, the only load in their path is this one. So they're going to dump all 12 Smarties here. So as they do that, they dump their 12 Smarties, return back to the battery to get more Smarties. The cars that travel this way, or the electrons in this path, they dump all 12 Smarties here because, again, the electrons that go this way, that's the only load in their path. So do you notice now how each car does not have to share its Smarties, right, with multiple loads? It's just hitting the one load that's in its path. So even though there are 3 loads here, the electrons that come across this load, those electrons only hit this load. That's the only load in their path. So the Smarties are not being shared, right? If one car comes this way, it's going to dump all of its Smarties. Doesn't have to share with these. The cars that come this way dump all their Smarties here. The cars that come this way dump all their Smarties here. And so in this way, the electrical energy is not shared. Now, what about the current? The current is the number of electrons flowing. So now, don't be thinking about the Smarties, the energy they have, just be thinking about the cars themselves. So you have cars leaving this battery, they all have to flow on the same path here, right? So all of these cars follow the same path. So they are not, that current is not shared, right? They all stay on the same path. So this current is not shared. Okay, that's my dog. Hang on a second. Okay, I'm back here. All right, so we decided then that the current, right, the number of cars leaving the battery here, right, all followed the same path. So the current did not, the cars did not split up. They just shared and followed the same path all the way around. Whereas in the parallel circuit now, think of the cars leaving here, right? The number of cars. So the current is like the number of electrons flowing. Think of it as the number of cars, right? So all the cars that leave the battery, some of them go here, some of them go here, some of them go to the third bulb. And so that current gets shared, right? The number of cars splits up there, right? To follow each path. And so the current gets shared. Okay, next part. What happens if we add loads? So the effect of adding loads. What's going to happen? Oh, I suppose I should back up here for a second and look at back up here to the energy, right? I just want to address, you've already done a gizmo with the series and parallel circuits. Just think of the brightness of the bulbs, okay? If we had 12 Smarties, right, with each car, and we had to dump 4 of them here and 4 of them here and 4 of them here, right? That's like having less Smarties, right, at each of these bulbs. So that would make these bulbs dimmer, right? So bulbs are less bright or dimmer. Whereas in this case, the cars that came this way dumped all 12 Smarties. So at each of these bulbs, the cars that get there are dumping the 12 Smarties, like all their Smarties, and so that would make these bulbs brighter. And now we're thinking about actually adding now we're thinking about actually adding loads. So we're going to add a bulb, right? And then we'll consider what happens when we remove one. So what happens when you add a bulb to this series? Okay, so let's, put another bulb right here, for example. Okay, so if we draw another bulb here, maybe I'll just do that one in black, let's say. Okay, we'll kind of add a bulb there. So now we've added a fourth bulb here. So think about, right, what the cars are going to do with their Smarties. They had 12 Smarties to start, and now they are going to have to dump Smarties 1, 2, 3, 4 places. So each car comes by and dumps their Smarties. You see how if they had 12 Smarties to start, they're going to be able to dump 3, 3, 3, and 3. So they'll dump their Smarties in these 4 places. And that means they're dumping less Smarties at each bulb because they had 4 bulbs to get to. So less Smarties, think dimmer, right? So, whoops, what's happening here? So the effect of adding loads, right? The effect of adding loads made the bulbs be dimmer, so less bright. All right. What happens in the parallel circuit? What happens if we add another bulb? So, I don't know, maybe we put another bulb here. Okay. So what would happen as we add another bulb here? Well, the cars that head this way still dump their 12 Smarties, right? There's other cars that head here and dump their 12 Smarties, but again, there's only one load on the path of the cars, the electrons that come this way. So if there's only one load there, they're going to dump all 12 Smarties. So we'll come back here and we'll just say that the effect of adding loads right here is that the bulb brightness, right, is like does not change of all of the other bulbs, right? They're all equally bright. The new bulb is going to be just as bright as the other ones, and the others don't change. Whereas in the case of the series circuit, they all become dimmer. Okay, now to consider what happens if we remove loads. So, heading back up here, if we were to remove, if we were to remove these loads, we'll need to consider, right, if we remove a load, right, and actually open the circuit, so let's think what happens. So if this bulb stops working, right, if you remove a load and the circuit is open, then the current can't flow and all the bulbs will go out. If we remove the bulbs and then close that circuit, right, then the remaining loads that are here, if it's a closed circuit, we just have 2 loads now, so they'll be brighter than they were before because the cars coming around only have to dump their Smarties at 2 places. So in terms of applications, and we think of this being used in a home, for example, if we have a bunch of loads on the same circuit in series here, right, the idea is that if one of the loads stops working, right, then the other loads also stop working. So really when I'm asking the question about removing a load, I'm really talking about if you've opened the circuit. So if you open the circuit here, then the rest of the bulbs don't work. What happens in the parallel circuit? If we go to remove loads, maybe I'll remove this one, right, and remove another one. Do you see how there is still a path for electrons to flow to this bulb and to this one? So the idea is that if you remove a load here, right, so you essentially open these 2 paths, so electrons can't flow there, the electrons can still make their way here and here. And when they get there, when those cars get there, they're still dumping their 12 Smarties. So you remove light bulbs or loads from a parallel circuit, you're not going to change the brightness of these other ones, right? They're still going to be glowing and they're still going to be as bright as they were before. But if you remove a load from series, so if you essentially open the circuit, then these bulbs turn off. So let's go back here and just recognize now that if you remove loads here, right, you open the circuit and all loads are off, right? Or the bulbs are not lit. Whereas if you if you remove loads from the parallel circuit, right, again, the remaining bulbs glow equally bright, like as bright as they were before. So there's essentially no change. Okay, so maybe we'll make that point that there's no change. All right, and so that kind of leads us into the last piece here, right? That if the loads are on or off, the idea that just recognizing that because all these loads are in the same path in a series circuit, right, they're either all on or they're all off. So we'll just make that point that these devices or loads, right, they're either all on or all off. Whereas in the case of the parallel circuit, we could have some of these be off, right, if they've been removed, or there's switches in place to be open, right? But if you have other paths, right, to other loads, as long as those switches are closed, if you have a switch in here, as long as it's closed, right, these paths are still available to be lit. And so that becomes super useful in a house, right, because you might have your toaster and kettle plugged in to one outlet in your kitchen. So let's say here's your toaster and your kettle. So if something happens to that outlet, right, then neither the toaster nor the kettle are going to work. But you may have your refrigerator and your stove on two different paths, right, in a parallel circuit. So maybe if the refrigerator stops working, that doesn't stop the oven or the stove from working. So appliances that are connected in series, right? If one doesn't work, then the other one doesn't work. Whereas appliances that are connected in parallel, right? You could have one be on and one be off at the same time. So we'll just make a point here, right? So loads on or off, right? So you can have one on or off, right, at the same time. So that's, very flexible and definitely has its place when you're wiring a home. Okay, so hopefully this has given you, right, some, a good understanding of how we analyze series and parallel circuits. It's not easy. I encourage you to build your understanding by thinking about the electrons as being cars and the energy of those electrons as being the smarties that are in the car. Okay, so again, the idea that electrons leave the battery carrying a certain energy, right? So they're like cars leaving this garage carrying a certain number of smarties. Okay, and just think about how the cars drop their smarties, right, to make the light bulbs glow, right? And also think about where the cars can travel. So we're thinking about the paths that the cars can travel, right? In a parallel circuit, there's multiple paths, and we're thinking about the number of smarties that the car has to drop, right, in its path. So if there's a number of loads in that one path, the car is going to have to drop a little bit of smarties at each load. Whereas if the cars that come across, right, only one load in their path, they can dump all their smarties at the one load and return to pick up more energy. Okay, good luck with this.